Hello and welcome to Unit 9, Lesson 2. Today we're going to be taking a look at potential energy diagrams. So lots of graphs today. Well, just one type of graph, a potential energy diagram. But there's a lot of information packed into this graph. So the whole lesson is basically just going to be about analyzing the graph for all the different pieces of information that we can pull out of it. So learning intention is, it looks a little bit long, right? Because I listed everything that we're going to take out of these potential energy diagrams. So a potential energy diagram, right, it's a diagram for the potential energy change in a chemical reaction. So we're going to analyze them for the direction of energy transfer, which is, right, a fancy way of saying, is it exothermic or endothermic, energy going out or in. The enthalpy of the forward and reverse reactions. Okay, that's the delta H, right? The activation energy, which we'll talk about. The energy of the activated complex, which sounds fancy, but I promise you is not. And finally, we'll look at the effect of a catalyst on the reaction in terms of the potential energy diagram. Okay, so for a do now today, a couple questions here. One is, well, they're both kind of review questions, right? Number one is a review from biology, living environment. Number two is a review from yesterday's lesson. Okay, so go ahead, pause the video and see if you can answer these two questions. Okay, so number one, an enzyme, if you remember, is basically, it's a biological catalyst, right? These are biological molecules that speed up chemical reactions, right? They do that by making it take less energy to start the reaction, so the reaction proceeds quicker. Okay, so we're going to be talking about catalysts today, and it's if you think about it, you can think of it as an enzyme. An enzyme is a little more complex, right? It's a biological. I believe they're proteins. I think. Don't quote me on that. But it's a biological catalyst. But they're doing the same thing. So an enzyme speeds up a reaction in a biological system. A catalyst is a little more generic, meaning it speeds up a chemical reaction. So a catalyst is anything that speeds up a chemical reaction, which we will talk about soon. Number two is a review from yesterday. So if you remember, delta H for a reaction. Remember that delta, the triangle there? That just means change in, right? So we're talking about the change in kind of the enthalpy, or you can think about it as the energy contained in the products and reactants, right? So over the course of a reaction, okay, if we want to measure the change in enthalpy, we take the enthalpy of the products and subtract the enthalpy of the reactants, okay? So delta H is equal to the enthalpy of the products minus reactants. So products minus reactants, okay? Keep that in mind. Okay, so let's dive in here. So potential energy diagrams. A potential energy diagram is a graph that plots the change in potential energy that occurs during a chemical reaction. So here's a very generic potential energy diagram. Notice how there's no numbers on the axes, right? So it's generic. And if you look at it's always important to look at the axes when you examine a graph, right? So on the x-axis here we have a reaction coordinate. Now what does that mean? It just means it's basically time. So it's like this is where the reaction starts, and this is what happens as the reaction goes on, okay? So it's like we start a reaction, and as we go from left to right, the reaction is proceeding, right? The reaction is actually reacting. And then on the y-axis, we have potential energy. So you see this line represents the change in potential energy as we move through the reaction, okay? Potential energy of the components, right, of the chemicals in the reaction that we're talking about. Okay, so you notice that there are some, we got A, B, C, D here, right, labeled on the graph. Now these are important ranges here, important points. So let's look at these real quick. So A, right, if we think about it, we're starting here, right? So A represents the potential energy of the reactants, right? The potential energy of the chemicals that we're starting with. Okay, that's because that's where we're starting the graph, right here. B represents the activation energy, right? So what is activation energy? Well, it's the energy required to start a chemical reaction. If you remember from yesterday's lesson, we looked at a reaction that where we had hydrogen and oxygen gas in a balloon, and we put a candle near it, right? A little bit of spark, just a little bit of energy, and then an explosion happened, right? So that candle to start the reaction, that was the activation energy required, okay? And this diagram here could actually represent that explosion, right? Because what happens is we add the candle, increase so we need a little activation energy, but then, right, potential energy drops, meaning energy is released. But I'm getting a little ahead of myself. So we start here with the reactants. Remember, this is energy. We add some activation energy to start the reaction, right? You got to get up over this hill for the reaction to proceed. Okay, if you can't make it, if you don't add enough energy to get over the hill, the reaction won't follow through. It won't do anything. Okay, so at the top of this hill, right, this is where we have the reactants, but now they've kind of absorbed the activation energy. So they're going to look a little bit different, and we call this the potential energy of the activated complex. So don't worry too much about this, but it's a pretty interesting point in a chemical reaction, right? I mean, it happens almost instantly. It's so fast, we don't really know. But there is a moment, right, if you think about it, if you're taking chemicals to, like, say, you know, whatever it is, oxygen, hydrogen, gas, and you're turning it into water in a chemical reaction, there's a moment in time where you don't have hydrogen or oxygen gas and you don't have water quite yet. You have something in the middle. And that something in the middle is usually very high energy, right, which doesn't want to exist, right? Nature tends towards lower energy. So immediately that activated complex, right, which is this high energy kind of in between, it's like a hybrid of the reactants and the products. It has the highest amount of energy, and then it'll immediately, right, once you get to the top of this hill, you'll go over the hill and the reactants will turn to the products. But just for a moment, right, it's kind of like if you took a bunch of pictures of a reaction and these chemicals changing, you would see this weird hybrid of the products and the reactants combined before the reactants actually fully turned into the products. And that's what represents the top of this hill here. That's the energy of the activated complex, right? Very high energy, not sustainable, right? You'll never stop here. You can't, right? It'll immediately go down that hill and convert into the products, which gets us to D, right? D is the energy or the potential energy of our products, right? This is where we end. So reactants, products. The beginning of the hill is always the reactants. The end is always the products, okay? So a couple more things. So, oh, right, this is what I was saying. I got a little ahead of myself, but now it's, you know, you got it on the screen. So, right, it's like a halfway point, right? A transition state between reactants and the products known as the activated complex, very high energy. Finally, what does a catalyst do? Remember we said a catalyst speeds up a chemical reaction. Now, how does it do that? How does it just speed it up, right? Well, what it does is it actually lowers the activation energy required. So you get a little tool here. What ends up happening is when you add a catalyst, the catalyst doesn't get used up in the reaction, right? The catalyst just kind of is there. It speeds up the reaction by lowering the activation energy, and then after the reaction's done, the catalyst is still there. It's not part of the reaction. But what it does is it's going to lower this energy hill so that now it takes less energy to start the reaction. Okay, that was almost perfect. So when we, addition of a catalyst, right, I'll circle this so you know what the red means. Okay, the addition of this catalyst will lower the activation energy required to start the reaction. So if we think about that balloon example with the explosion, it's like, I don't know what the catalyst would be for that specifically, but it's like it would take less of a spark, right? Maybe I don't need a candle, maybe I just need some static electricity, or, you know, a catalyst would essentially lower the amount of energy required to start that reaction. Okay, so that means what's going to happen is it's going to speed it up, right? If you need less energy to start it, it's going to start more quickly. Okay, so that's a lot, so definitely review that if you like. Now, I'm going to use a real example, or half real, right? We've got some numbers here, but, right, we just have A, B, C, D. And we're going to analyze this potential energy diagram, right, for the different parts. So, Yeah, let's do this together. Okay, so what are the reactants in this potential energy diagram? So remember, reactants, always where we're starting, right? The starting point. So A and B are our reactants. Okay, I'm not going to write these. It's going to take me too long. Okay, A and B, they're our reactants. Okay, well, I got to finish this one. It's going to bother me. Okay, but I'm not doing it anymore. What are the products? Well, you can probably guess, right? That comes at the end. That's over here, C and D. Okay, so reactants is that first like little plateau type part, and then products are always the end. Okay. Now, here's a tricky one, right? We haven't talked about this. Does this graph represent an endothermic or an exothermic reaction? Think about it. Remember what we talked about, that delta H, right? Delta H is energy, or the enthalpy of the products minus the reactants, right? So look what's happening here. We're starting here at 40 kilojoules, right? That's the energy, that's the potential energy of our reactants, right? That's what we said. And then we're ending at 20 kilojoules. That's the potential energy of our products. So what happened to that 20 kilojoules between the 40 and the 20? Well, it gets released as energy, right? So if it's releasing energy, that means exothermic, right? So if your if your products have less energy than your reactants, that means energy was lost or it came out, right? And that's exothermic. An endothermic reaction, right, might end up high. It has to end up higher than you started because it would have had to absorb energy. Okay, number 4. Determine the heat of reaction, the delta H, for this reaction. Okay, so the delta H, right, is always the energy of the products minus reactants. Products minus reactants. So 20 minus 40 is negative 20. Negative. Now, I knew this was going to be negative anyway because it's exothermic, right? An exothermic reaction is going to have a negative delta H, whereas an endothermic reaction is going to have a positive delta H. So real quick review of these. Reactants on the left at the start of the diagram, products on the right. Okay. In an exothermic reaction, we're going to see that the products have less energy than we started. In an endothermic, which is not depicted here, the products will have to end up higher. Okay. And then heat of reaction is the same equation that we looked at, back here, way back here in the do now, right? Delta H it's the energy of your products minus reactants, so 20 minus 40 is negative 20. Okay, and again, I knew that was going to be negative because it's an exothermic reaction. Exothermic reactions always have negative delta H's. Okay, we got a few more questions here. So, determine the heat of reaction, delta H. I just did that. Oh, for the reverse reaction. Well, this one's simple. I'm not even going to think about it. If the forward reaction is negative 20, right, kilojoules, always put your units, right? Then the reverse reaction is positive 20 kilojoules, right? Because a reverse reaction is always the same value, right? Same amount of energy involved, it's just going in the other direction. Okay, that's terrible kilojoules, but yeah, that's what it is. So it's going to be positive 20, right? Whenever you're doing the reverse reaction, the delta H is the same number. It's just different sign, which we did in yesterday's lesson. Number 6, determine the activation energy for this reaction. So remember, the activation energy, you can think about it, it's like, if I want to get here to my products, I got to get up over this hill. So how do I get up over this hill? Well, I got to go from 40, in this case, all the way up to 100. So what do I have to add there, right? So here's our activation energy from here up to here. So how do I get there? Well, I would add 60. So the activation energy for this, or E sub A, right, is 60 kilojoules. Right, it's supposed to be a lowercase k. I'm just having trouble Okay, right, so there's our activation energy. And remember, it's not 100, right? The activation energy is not from here to here, it's from where we start to the top of the hill. However, number 7, what is the energy of the activated complex? That's the total energy at the top of the hill, and that's going to be 100, okay? So energy of the activated complex is just how much energy is at the top of the hill, right? You don't have to do any math. You just go to the top of the hill, go over, boom, it's 100 in this case, 100 kilojoules. Okay. Number 8, indicate how the presence of a catalyst would change the potential energy diagram above or to the right, whatever. So this is always the same, okay? It's always, a catalyst will always lower the potential energy hill. So it might go up to here and then stop here and then come back down. Okay, so it's always going to lower the hill. So when it says indicate how the presence of a catalyst would change the diagram, you always just make the hill lower. Now you could go down here if you want. You could go just slightly lower. It doesn't matter. As long as the hill is lower, you've indicated how a catalyst would change the diagram. Okay, it's never going to give you an exact number amount of change of potential energy. So all you got to do is just realize that the hill becomes lower. Okay, so that's it for this potential energy diagram. Definitely, go back through those quickly. And then once you're ready, we're basically going to do it all over again, but with a new potential energy diagram. Okay, so this is a good place to pause the video. You got 6 questions about this potential energy diagram. Try that challenge question if you're feeling bold. Okay, so go ahead, pause the video here, and I'll go over it as soon as you unpause me. Okay, so hopefully you tried this on your own and you're not just listening to this straight through. So let's analyze this thing. All right, is this reaction endothermic or exothermic? Well, if we remember, we have to look at our reactants and products. Okay, so here are our reactants, here are our products. And look, our products have more energy, right? We started with 50 and we ended up with 100. Right? That means during this reaction, the reactants must have absorbed energy to become the products because the products have more potential energy. So if you're absorbing energy, that's going to be endothermic, right? Endo goes in, energy goes into the equation. Okay, number 2, determine the heat of reaction, delta H, for this reaction. Okay, remember, delta H is always products minus reactants. So this is going to be 100 minus 50, which is positive 50, right? And I knew it was going to be positive because it's an endothermic reaction, and all endothermic reactions have positive delta H's, okay? All right, determine the heat of reaction for the reverse reaction. This should be immediate. Reverse reaction, I just changed the sign. This one's going to be negative 50. So remember, reverse reaction would be starting here, going this way, and going down to there. Right? Reverse reaction is exothermic because we're ending up lower if we're going backwards, right? So the reverse reaction is always the same amount, the same magnitude, right? Which is just what the number is, different sign, right? Opposite sign. Oh, nice little J there. Okay, number 4. Determine the activation energy for this reaction. Remember, activation energy, how much energy do I need to get up over that hill to start this reaction or to see this reaction through? So we're starting here at 50, okay, and we're going up to, what is this, 250. So from 50 to 250, how do I get there? Well, I have to add 200 kilojoules, right? So it's just about how do I get from where I start to the top of the hill. That's the activation energy required, and for this made-up reaction, whatever it is, it takes 200 kilojoules to get from our reactants to the top of the hill. At the top of the hill, that's our activated complex. And if we're talking about the energy of the activated complex, that's the total energy. So I just go to the top of the hill, go over, 250. Okay? So the energy of the activated complex is 250 kilojoules. All right. Finally, indicate how the presence of a catalyst would change the potential energy diagram. Guys, this is always the same. Right? It's going to lower the hill. Now you could lower the hill a lot, right? If you want. That's not bad. That's a pretty good one. Or you could lower the hill just a little bit. Anything in between, totally fine. Okay? As long as it's lower than the 250 mark, the top of the hill, as long as you lower that, that's how a catalyst would change the potential energy diagram. Okay, so that's the end of this lesson. Definitely a homework on this one. Make sure you try that so I can get some feedback. You can end the video here if you like. I'm going to move on to the challenge question if you tried that one. It's a little bit more involved, so it's going to add about maybe like 5-6 minutes onto this video. But if you're good to go and you want to start the homework, feel free to end the video now and get started on that. Okay. All right, so if you stuck around for the challenge question, it asked us to draw a potential energy diagram with the numerical values for the combustion of methane. Okay, so first of all, right, I'm just going to get my diagram started here. I know I'm going to have that and that. Over here is potential energy, right? Down here is reaction. Right? It's a short term for reaction coordinate. Right? This is also just the progress of the reaction, right, as we go from left to right. Okay, so we do need some information, right? Because it's the combustion of methane. So if I look at table I and I find the combustion of methane, which is right here, right? I see that it is, look at that, negative delta H, negative, that means it's exothermic, and it's negative 890.4. So, I know it's exothermic, so it's going to look something like this. Oops. Yep. Okay. This could have been better, right? I was going to end it there, but then I realized, oh, that would have been endothermic because if you end up higher, that's endo because you had to add energy. So I ended up way lower, right, than we started, so to make it exothermic. Okay? So over here we have our reactants, CH4 and O2, and down here we have carbon dioxide and water. Those are our products, right? So our products end up with less potential energy than our reactants. Okay? Now it does say it wants me to put numerical values in. So I don't know the starting potential energies of each of these, but I do know the difference because the difference is the delta H, right? So I know from, let me go back to my thing. So it's negative 890.4. So since my delta H is negative 890.4, okay, I know that the difference between here, so that's, right, and here is 890.4 kilojoules. Okay? So that's the difference there. Now, I'm not sure what the exact numbers are to start and end, but I know the difference is 890.4 kilojoules. Okay? So if you did anything like that, right, if you, a few key points. If you made the endpoint lower and didn't make the mistake that I almost made, right, that's pretty awesome. If you notice that the difference here is 890.4 kilojoules, that's fantastic. Okay? Other than that, and if you put in your reactants and products. Okay, so your diagram hopefully looks a little cleaner than mine, but that's basically it. All right, and that's the end of this video. I'll see you all tomorrow.